Hello, Calc friends. Welcome to today's lecture online. We're going to be talking about the cross product. So what do we have? So last time we talked about if you have two vectors u and v, we can take their dot product u dot v, and just a reminder what u dot v was equal to. It was, I think, defined to be the magnitude of u times the magnitude of v times the cosine of the angle between them. But we also found that that was equal to just the sum of their components. So it was like u1 v1 plus u2 v2 plus u3 v3 if they're three-dimensional vectors, so on and so forth. And that was one way to find their product. And the question is there another product? Like, what is so special about this kind of multiplication? Is there another multiplication or product? And it turns out there is. This product right here is sometimes called a scalar product because the result is a number. But there's actually a vector product where the result will not be a scalar, but will be a vector. And so let's take a look. How do I should probably, so let's get some motivation on where this idea of a vector product comes from. And so it comes from if the idea of torque. And so if you have, let's say, a wrench attached to a screw, and if you have kind of the wrench can be represented by this vector r, and then you put a force on that wrench represented by this vector f. So f is kind of the force you put on the wrench. And the idea is that as we apply this force, it's creating this kind of third force called torque. And the torque is kind of the amount of push that comes from the twisting of this wrench. And so it's almost like a twist force. And it has to do with kind of this vector r and then a component that's perpendicular to that vector r. And so we get that the torque T is actually equal to the magnitude of r times the magnitude of f, and not the cosine between them, because it's the component that's actually perpendicular. And so if this is the angle theta, or I guess by parallel, this angle theta will be the same as that angle theta because of parallel angles. And so if this is 90 degrees, then this is the opposite side. And so it's actually going to be sine theta. And so this is the cross product. And so T, or torque, that's tau, is equal to the cross product. Whoops. Is equal to the cross product. And so actually this would be actually the magnitude of tau. Tau is equal to R cross F in a certain sense. So I don't really know what else to say about it from that sense, but it's just it's another type of product. When you have two vectors, we can take their product and it's actually going to return a vector because this torque is actually a vector too. It has a direction, not just a magnitude. Whereas the dot product just had a magnitude, and so it was just a scalar. So how is the dot product or the cross product defined? The cross product will be defined, will be defined such that the magnitude of the cross product will be the magnitude of u times the magnitude of v times the sine of the angle between them. The way we actually find the direction is a little bit wonky or weird, but the idea is that the cross product vector is always perpendicular to the two vectors that it's the cross product of, and we're going to use the right hand rule. So if you put your palm the direction of u and curl your fingers towards v, then your thumb will point up in the direction of the vector. And so I can show you guys that again in class when I do it in person. But the idea is that put your palm on U, curl your fingers towards V, and then the direction your thumb is pointing is the cross product. How we actually find this vector, we're gonna have to come up with a better way because yeah, the sine of theta makes it kind of annoying, but just like with the cross product. Some things about kind of what the geometry of this represents. If vectors u and v are parallel, then their cross product is 0. So if u and v go in the same direction, then the sine of the angle between them is 0, and then the cross product will be 0. If u and v are two sides of a parallelogram, then actually the area of the parallelogram is just the magnitude of the cross product. And that comes from actually a really simple kind of proof here. If you have a vector u and a vector v and an angle between them, then this side length right here is actually the magnitude of v sine theta. And then this is magnitude u. And so then the area of this parallelogram is that length times that length. And so it's just u cross v. And so this is an important idea, though, that the area of a parallelogram is the magnitude of the cross product. So area of parallelogram, I'll write it again, parallelogram is equal to the magnitude of U cross V. And so the magnitude of a cross product kind of gives us this area of a parallelogram. Some properties about the kind of algebra of cross products. If you do a cross product and switch the order, it becomes negative. That's because of the right hand rule. So if I start here and cross this way, then my thumb's actually gonna point down, and so it points in the opposite direction. So switching the order does matter. Scalars can pull out. So if you have a scalar here, it pulls out. If you have a scalar here, you pulls out, and so it can go on both. If you do a cross product plus an addition, it distributes, and then it distributes the other way too. So the idea is that all this stuff is great for magnitudes if we have a theta, but what about direction and components? And so we need to actually talk about what the cross product is of the three basis vectors I, j, and k in order to find what it is for an arbitrary vector. And so the way you can do the right-hand rule is if you first do I, which I believe is this direction, and then you cross your fingers towards j, then your thumb will point up towards k. So I cross j equals k. So that gives us that. If you do j and then curl your fingers up towards k, your thumb will point towards I. So j cross k equals I. And if you do K and curl your fingers towards I, your thumb will point towards J, and so K cross I is J. And so we have a handy dandy little thing right here. And so this is the cross product of the coordinate vectors. So I cross J equals K, J cross K equals I, and K cross I equals J. They kind of go in order. So if you do I to J, that gives you K, J cross K gives you I, K cross I gives you J, that kind of idea. Okay, now we're in a position to actually prove what or compute what a cross product is. And that's what I'll spend the remainder of the time doing. So let's say you have two vectors u and you have vector v. So that's components u1, u2, u3, v1, v2, v3. Another way we could write this is u1i plus u2j plus u3k. And this one's v1i plus v2j plus v3k. And now we're going to use this distributive property here, those two distributive properties, to actually write what their cross product is. And so U cross V will be that cross that. And then using the distributive property, we get U1, V1. So it becomes that guy and that guy, I cross I. U1, V2, I cross J. And so you just kind of do the distributive property to every single one, and you'll get 9 products. And then we look at what I cross I is, I cross J is, I cross K is, so on and so forth. And if you simplify it all down, so this one is 0, so it goes away. That one's 0, it goes away. That one's 0. And then then you collect like terms, right? So the ones with the I are that guy and that guy. And so we're going to get U cross V will equal, for I, we get U2 V3 minus U3 V2. That's the first component. So that's the I component. And then it will be, for the J component, it will be this minus this. So it's going to be U3 V1 minus U1 V3. So it'll be plus U3 V1 minus U1 V3 J, and then plus for the K components, it will be U1 V2 minus U2 V1. U1 V2 minus U2 V1. I should move this over. And that's a K. And so that's pretty complicated to do. And so to remember it, we use what's called the determinant of 3 by 3 matrix. So if you've seen this before, awesome. If you haven't, I'll teach you. It's really not that hard. So the idea is that a matrix is a 3 by 3 array of numbers. So the rows are the A, B, and C, and then the columns are the 1, 2, and 3. And so A1 is like first row, first column, A2 is first row, second column, so on and so forth. And then the idea is to take a determinant of a 2 by 2 matrix. The determinant of a 2 by 2 is just A, B, C, D. You do this cross product, or this multiplication, AD, and then you subtract that multiplication. So the determinant of a 2 by 2 is AD minus BC. And then we use what's called cofactor expansion to do the product of a 3 by 3. And so we expand along the top row. So A1 goes here, A2 goes here, A3 goes here. And you'll notice the coefficients are plus, plus, minus, plus. The reason for that plus, minus, plus is because the determinant is what's called an alternating function, but don't really worry. It's just whenever you cofactor expand along the top, it's going to go A1 minus A2 plus A3. So it's that one minus that term plus that term. And then you're going to cross out. So when you do the A1, you're going to cross out his column, his row, and then you're going to take the determinant of what's remaining. And so the determinant of what's remaining is B2, B3, C2, C3. And to take that determinant, you cross that and take their difference. And then you're going to do minus, cross out his column, his row, and what's remaining is the B1, C1, and B3, C3, and that's what's there. And then for the A3, you cross out his column and his row, and you have that remaining. And so it's B1, B, C3, B2, C2. Doing all that with the following setup here. So this is how you do a 3 by 3 determinant, and then this is how you use it for a cross product. So for the cross product, we're going to do you put the first components in the second row, U1, U2, U3, and the components of the second vector on the bottom one. And so this will equal, you take I, and then you take the determinant of crossing out his column and his row, and you get U2, U3, V2, V3, but the determinant of that is U2 times V3 minus U3, V2. And so you get U2 times V3 minus U3, V2. And then it's minus J times crossing out his and his, you get U1 V3 minus U3 V1. U1 V3 minus U3 V1. And then finally plus K, crossing out his row and his column, you get U1 times V2, U2 minus V1. So it becomes U1 V2. U1 V2 minus U2 V1. And so that's the cross product. And so the cross product of U cross V is this, which is equal to this, which then that simplifies down to what I wrote right here. So let's do an example. Let U be that vector, V be that vector, find the cross product and the magnitude of the cross product. So by definition, U cross V is equal to the determinant of I, J, K. So that's the first thing, right? Then you write the components of U, which is 1, 0, 1. Then you write the components of V, which is 0, 1, 1. And now we take the determinant. And so you take this determinant times I. And so that's going to be 0. So I'll just write it as 0 minus 1 times I minus, now we're going to cross out his column, his row, and take the determinant of that. That gives us 1 minus 0 minus 0j plus cross out his column and row, and you get 1 minus 0. And so it's 1 minus 0k. And so this vector becomes -1, -1, 1. So that's their cross product, -1, -1, 1. Then the magnitude of that vector is just going to be square root of 3. So that's the magnitude of the vector. And so you have two three-dimensional vectors, their cross product, which is a vector that is perpendicular to both of them. So this vector is simultaneously perpendicular to those two guys. And then its magnitude is √3. Okay. Now let's do another example. Area of a triangle. Let's say we have a triangle with vertices 0, 0, 2, 3, 4, and 3, 2, 0. Then the idea is that they actually form a parallelogram. If you take the vector from O to P and the vector from O to Q, that makes a parallelogram. And so the area of the triangle is half the area of the parallelogram. So area of triangle is 1/2 area of parallelogram. But we know the parallelogram, which is equal to 1/2 the cross product of OP cross OQ. And so we need to find the cross product of OP, OQ. OP, the vector that goes from the origin to P, is just the coordinates of P, written as a vector. And then OQ, it's the vectors of Q, which is 3, 2, 0. And so we just need to find the magnitude of their cross product. So we're going to compute their cross product. So OP cross OQ is equal to I, J, K, 2, 3, 4, 3, 2, 0. So if you do the I term, you get minus 8I. If you do the J term, canceling that, and that's 0, and that's it's going to be minus, because the J term is always minus, and then or it starts out negative, and then 0 minus 12, so it'll be negative 12J, and then plus the K term will be 4 minus 9. 4 minus 9J. And so we get negative 8, 12, 5. So negative 8, 12, 5. And then that, the magnitude of that, so then the magnitude of OP cross OQ will be equal to, I guess I'll just do 1/2. It'll be 1/2, and then square root of 64 plus 25 plus 144. I don't know if that's anything. That's 169 plus 64. I don't know what that is. 1/2. 169 plus 64. 173 plus 60 is 233. So that's the answer. I don't know if that's anything special, but I think that's right. 9, 8, yeah, 233. So that's the answer. That's the area of the triangle. Nothing crazy, nothing special. Now, another thing that you can do with cross products is it gives you a vector orthogonal to two vectors simultaneously. So find a vector orthogonal to the two vectors there. And so you just take their cross product. Their cross product will be orthogonal to both of them. So U cross V is going to be I, J, K. -1, 0, 6 are the components for U. Components for V or J are 2, or sorry, for V is 2, -5, -3. So for I, you get 0 minus -30, so you get 30I, minus, if you do J, you get 3 minus 12, which is minus 9J. And then for K, you get 5 minus 0, 5K. And so our vector will be 30, 39, and 5. That will be a vector that is orthogonal to both of them, or negative, right? You can take the negative of that, would also work. So is orthogonal to both. Orthogonal to both. Or you could take the negative, -30, because that will be the vector going in the opposite direction, is as well. Finally, the last thing we'll talk about is application of torque. So with torque, you have a radial force that you're applying that's kind of like acting as your arm or your fulcrum or whatever. And then you have a force applied to the tip of that vector. And then the torque is just the cross product. And so let's say we have a tip of a lever at the point 1, 1, 1, has a force of that applied to it. Compute the magnitude of the torque at the origin. And so the idea is that R is going to be the vector 1, 1, 1, because that's kind of where the tip of the lever is. Our vector F is 3, 2, -1. And so then they're cross product. So the torque, the magnitude of the torque is just equal to the magnitude of their cross product. And so we compute their cross product. So R cross F will equal I, J, K. And then you get 1, 1, 1, 3, 2, -1. Oops. So we take the magnitude of that. Or sorry, you take the cross product and you're going to get -1 minus 2. So you get -3I minus the j term will be -1, -3, so -4j. And then k will be 2 -3, so it'll be -1k. And so that's the vector -3, 4, -1. And so then the magnitude of r cross f is the magnitude of that vector, which is going to be the square root of 9 plus 16 plus 1, which is √26. So that is the magnitude. The magnitude will be that, and you could also use that to find the angle between them too if we wanted to, but we don't really need to. I guess I didn't actually ever say that you can use this to find, you could use the cross product to find the angle between them too using sine, but that's not actually that big of a deal. All right, that's all I got. I'll see you guys on Friday. Take care.